Hello, my name is Kevin Lanaugh, and today I'll be presenting the paper that was written by NASA Goddard Space Flight Center team led by Dr. Serhat Olnik, and my name is Kevin Lanaugh, and I led the Vulcan Wireless team, and the paper is entitled S-band Transponder Multi-Network Compatibility, Space Environment, and Radiation Testing. This paper presents the testing of the software-defined radio transceiver, the NSR SDR S/S, that's manufactured by Vulcan Wireless, and it meets the emerging needs for versatile small satellite communications and navigation solutions. Vulcan Wireless and NASA Goddard Space Flight Center collaborated in testing this radio for a wide range of mission sets. The missions that are currently being supported by NASA Goddard Space Flight Center CubeSat missions is the PetiteSat, Snoopy, GTOSat, BurstCube, and Dione, and the different missions range on downlink data rates up to 4 megabit per second, and uplink data rates ranging up to 62.5 kilobits per second, and those will be supporting the NASA Near-Earth network in low Earth orbit profile, and two of the missions will be using two waveforms, the Near-Earth network and the TDRS multiple access network, and those missions will be using not only the Near-Earth network capability, but also 1 kilobit per second range data rate for the TDRS multiple access network. The multi-network RF compatibility was performed on the NSR SDR S/S radio, which has basic features and functionality of full duplex with 4 watts RF transmission, the unified S-band frequencies, and the Near-Earth network waveform, which will have multiple uplink and downlink data rates ranging from 1 kilobit to 4 megabits per second. The NASA Space Network will be using the tracking and data relay satellite system on the multiple access interface, which uses a spread spectrum waveform and has multiple data rates forward and reverse, but will be using the 1 kilobit per second data rate. The Near-Earth network compatibility testing will be done in the full duplex functionality under simulated space link dynamics. Waveforms that will be used in the mission are tested to validate on-orbit performance and ensure the quality and reliability over the full RF regime. The physical layer testing will be done on the transmitter, and it will be testing over the full frequency ranges and power levels, modulation characteristics, forward error correction, and symbol rates. Virtual channel performance will be tested in the, this diagram kind of gives you an idea. The radio is set up with a simulated flight computer communicating data, which is then turned to RF, which will transmit down to the ground, what they call the ground system environment testing, and it will be done through an RF interface. The physical layer testing for the receiver will also tune over the frequency range and will be tested over the full range of power levels to support the mission, as well as the Doppler shift to accommodate the full acquisition and tracking ranges for the mission sets. Demodulation bit error rates will be tested, protocol formatting, as well as command link transmission units. The Near-Earth network RF link analysis was performed to verify that the link will be a suitable margin over the full range of mission sets. So I've color coded those in this particular graph, and it shows on the upper portion the uplink with link margins, tremendous link margins because there's large ground terminal, so that's no problem there. The downlink will be also shown over all the data rates to be supported with very large link margins also. And it shows that for both the 4 watt and the 1 watt functionality on the radio, those power levels. Okay, let's go to the next one. The space network is the next waveform that we test, conduct the compatibility testing. And in this case here, we're going to be testing the DG1 mode 2, which is a spread spectrum for forward and reverse links with a high chipping code rate This is done so the system can support multiple users simultaneously. The forward link, which is a link coming at you, must synchronize and despread the signal to recover the message that's being transmitted. And then the return link also spreads the data with a chipping sequence, again, to support multiple users. Test the full duplex capability of the radio under these simulated space link performance. Waveform that will be used in the mission are tested to validate on-orbit performance. This ensures quality, reliability over the full RF regime. The physical layer testing for space network is done at the frequency that the system operates at the transmit power levels, modulation characteristics, and forward error correction symbol rates. Virtual channel performance is also tested. Okay, on the receiver side, we test the receive frequency, input power levels, Doppler shift for acquisition and tracking, demodulation, bit error rates, and same thing, protocol layer, as well as command link transmission unit. So here we also performed the space network RF link analysis. And so on the multi-access forward link, which is shown in the upper portion here, we show the multiple data rates, and you can see that we have very limited margin at the 3.9 kilobit per second, but we lose margin at the higher data rate. So we will be, the link that has margin is the 1 kilobit per second. So that's what we'll be using for that link, that system. Let's go to the next slide. We also are going to do environmental testing that tests vibration, which will be done over random vibration. That'll be done over levels that are appropriate with the launch that will be, a launch provider will give us that profile. And then the thermal vacuum testing is done to basically accelerated life testing for the hardware. And so there'll be multiple cycles done. On radiation testing, we simulated the space environment for low Earth orbit. And in this particular case, I'm pointing out a 5 millimeter shield with 0.1 K-rad total integrated dose. Let's go to the next slide. For the geo environment, we have simulated 100 K-rad for the operational environment. So in that case, we're going to be testing the total dose up to those levels to validate the system will perform at those levels. Further, we'll be doing single event testing, which is what they call, referred to as heavy ion beam testing. So that'll bombard the test article with ion beam of linear energy transfer levels that will simulate the single event effects that we're interested for our space environment. And the system that we'll be doing this with, the ion beam, will have variable variable species, energy, and flux fluence levels to simulate the single event effects we're interested in for our mission profile. These levels mimic on-orbit rates of upset to simulate real-world operational conditions. In conclusion, the results of this effort will be a fully tested communication solution that'll support 5 CubeSat missions. It'll leverage Goddard Space Flight Center's extensive testing facilities and this will be a very efficient and economical test because it'll be used over a wide range of these 5 missions, so the cost will be divided out to give maximum leverage and capability for the missions that are going to be flying. So it also solves the multiple waveform functionality that will be used for each mission, giving them a wide range of capability. And in the final report will demonstrate and document highly reliable, robust communication solution for multiple CubeSat missions. I'd like to thank you for your time and enjoy SmallSat, the SmallSat conference, the 34th annual event. Thank you so much.